This is a force example problem of finding the stopping time for a skidding car. Here's the problem we're going to be looking at. Oh no! You accidentally drove past the ice cream store and you really want ice cream. You slam on the brakes, locking the wheels and skidding to a stop. You were going 15 meters per second when you started braking. If the coefficient of friction between your tires and the road is 0.95, how much time does it take to come to a stop? Alright, that last bit sounds a little bit like a kinematics equation, but in order to solve almost any kinematics equation, I need to know something about acceleration, and I know that force is related to acceleration through Newton's second law, that the sum of the forces acting on an object equals the object's mass times its acceleration. And so this is going to be a problem about finding all the forces acting on the car and determining the vehicle's acceleration. So I'm going to begin by visualizing the problem. Here's a road, and here's my version of a car. And if I draw a boundary around the car, any place where there's a contact, there's going to be forces. And so between the car and the road, there is going to be a force of friction, which is going to be acting to slow the car down. There's going to be a normal force that comes from the road acting on the car, and that normal force is in response to the weight of the car pressing on the road. Let's go ahead and make our free body diagram. So there's just a dot which represents the car. There's a downward directed weight, an upward directed normal force which comes from the road pressing on the car, and then a force of friction which is going to be kinetic friction because the vehicle is actually sliding against the road. So I can set up an area for side work where I make notes, do unit conversions, just kind of organize my thinking in a less formal way. I know something about the force of kinetic friction. I know that kinetic friction is always equal to a coefficient of friction times the normal force. And I know that weight is the force of gravity acting on an object, and so that's m times little g, the local gravitational acceleration. I can't really expand on normal force. Normal force just depends on the force that the surface is experiencing. It's a reaction force. So now I'm going to go ahead and make a table. So I'm going to write down every force in the problem. So that will include normal force, weight, and the force of kinetic friction. And now I'm going to break it down into x and y coordinates. I can go ahead and make a note to myself about my coordinate system. X is horizontal, y is vertical. I can also make a note to myself about the net force, which I know must be working to slow the car down. So I want to consider my forces which are acting in the x direction. Normal force does not act in the x direction. Weight does not act in the x direction. But kinetic friction does, and I can go ahead and write down the expanded form of that. So the coefficient of friction times normal force. And this is acting in the negative x direction, so I should add a negative sign. So now I will consider my y components. My normal force is acting in the positive y direction, and my weight, mass times gravitational acceleration, that's acting in the negative y direction, and friction does not act in the y direction at all. Now it's time to add things up. And so to give myself some room, I'm going to write things down over here. The sum of the forces in the x direction is simply equal to negative mu sub k times the normal force. And according to Newton's second law, this should also be equal to the mass of the object, the mass of the car, times its acceleration in the x direction. And since I know the car is coming to a stop and there's a net force in the x direction, that acceleration is non-zero. Now the sum of the forces in the y direction is equal to this positive normal force, and then I can subtract the weight, and that is going to be equal to the mass of the vehicle times the acceleration in the y direction. But I know that it's not accelerating in the y direction. The car is not accelerating into or off of the road, which tells me that this normal force minus the weight mg is actually equal to 0. So I'm about out of room. I'm going to have to continue this problem on the next page. Alright, this is as far as I had gotten on the last page. I had discovered that in the x direction, the force of friction is the only thing acting. It's producing this acceleration in the x direction, whatever that is. In the y direction, there's a 0 acceleration, and so the net force, the normal force minus mg, which is the weight, should give me 0. I can look back at the problem. It's asking me about a time, but earlier we had decided that in order to find the time, I needed to find the acceleration. So at this point, I'm focusing on solving for acceleration. It doesn't look good. It's a little bit unnerving. I've got masses in a couple of places, and I don't know the mass. It wasn't given in the problem. But don't give up yet. We're not done yet. Looking at the y component side, I can add an mg to both sides, which means that the normal force is equal to mass times the gravitational acceleration. This gravitational acceleration now, or I'm sorry, the normal force shows up over here. I can substitute in. So negative mu sub k times mg is equal to the mass of the car times its acceleration. Those masses can cancel. I can divide by mass on both sides, and they disappear. Now I'm down to stuff that I do have numbers for. This whole factor is negative. It's not the coefficient that's negative, it's the whole thing. So negative 9.5 times 9.8 meters per second squared. That's going to be equal to the acceleration in the x direction. And when I work that out, I find that negative 9.31 meters per second squared is the acceleration in the x direction. That negative sign comes from the way I set up my coordinate system. I'm not quite done. I need to find the time. So I am going to use the fact that this acceleration is equal to the change in the x velocity divided by time, which means that the time is equal to the change in x velocity divided by the acceleration. The problem did tell me that I was going 15 meters per second when I began braking, and I know that I come to a stop, which means that the total change in x velocity is a negative 15 meters per second. And I divide by my acceleration, which is a negative 9.31 meters per second squared. And so this is going to wind up giving me a time of about 1.6 seconds. And I have solved this problem.